There is a kind of violence happening right now, all around you, scattered across the observable universe in numbers too large to fully comprehend. It is happening in the hearts of galaxies, billions of light years away. It is happening 30,000 light years from where you are sitting, at the center of our own Milky Way. It is happening in binary star systems strewn across the spiral arms of countless galaxies, where one star slowly, inexorably, devours the outer layers of its companion. And it is happening with an intensity and efficiency that makes our sun, with all its nuclear furnace, roaring at 15 million degrees in its core, look like a candle flickering in the wind. You cannot see any of this with your naked eye. The sky you look up at on a clear night appears calm, almost pastoral. A scattering of familiar constellations, a slow procession of planets, perhaps the pale river of the Milky Way, arching overhead if you are far enough from city lights. Nothing about that quiet panorama suggests the scale of the processes unfolding within it. The universe's most extreme events are either too slow for human perception, too distant, or operating at wavelengths our eyes were never built to detect. What we are going to explore tonight is a structure that sits at the intersection of the most powerful physics in existence, the accretion disk, specifically accretion disks around black holes. These are not simply rings of dust, the way Saturn's rings are rings of ice and rock slowly orbiting a giant planet. An accretion disk around a black hole is something far stranger and far more energetic. It is a swirling, superheated ocean of plasma and gas, stretching from thousands or even tens of thousands of kilometers at its outer edge down to a boundary so close to the event horizon that the physics we use to describe everyday reality begins to buckle and warp. Matter in these disks moves at velocities that are a substantial fraction of the speed of light. Temperatures in the innermost regions reach into the hundreds of millions or billions of degrees. The radiation pouring outward from the innermost zones is so intense that around the most massive and actively feeding black holes, it can outshine every single star in an entire galaxy, all the hundreds of billions of suns, combined by factors of hundreds or thousands. This is not a thought experiment. We have seen it. We have measured it. We have in recent years even photographed the shadow of a black hole surrounded by just such a disk, a glowing ring of superheated plasma hanging in the darkness 53 million light years away. Its image carried to us by radio waves, collected simultaneously by telescopes, spread across the entire Earth. The story of how matter spirals into a black hole's grip and what happens to it along the way is one of the most compelling narratives in all of modern science. It touches on fundamental laws of physics that govern everything, from spinning ice skaters to the formation of planetary systems. It involves magnetic fields so tangled and turbulent that they drive enormous flows of energy outward even as matter falls inward. It involves jets of plasma launched at nearly the speed of light, shooting for hundreds of thousands of light years through the void of intergalactic space. And it ends, for every particle of matter that crosses the final threshold, in a transition so absolute and so strange that our mathematics can describe it only incompletely. So settle in. We are going to follow matter from its peaceful beginnings as interstellar gas, through the spiral, through violent heating, and through the boundary of no return. We will examine why these structures are the most efficient engines in the known universe, outperforming nuclear fusion by factors of 5 to 60. We will explore the jets they launch, the famous individual systems we have studied in detail, and the history of how human beings went from having no idea these objects existed to capturing their first photograph. And we will end at the innermost edge, the place where stable orbits cease to exist, and where the universe keeps some of its most carefully guarded secrets. Before we go any further, if you find this kind of deep, unhurried exploration of the cosmos meaningful, a like or a subscribe helps the channel enormously and means more journeys like this one. Let us begin. To understand accretion disks, you first need a clear sense of the objects that create them. Black holes are not simply very dense stars. They are regions of space-time where the curvature of reality itself has become so extreme that not even light can escape if it finds itself below a certain threshold. That threshold is called the event horizon, defined by the geometric condition that the escape velocity equals or exceeds the speed of light. For a black hole with the mass of our Sun, the event horizon would be a sphere roughly 3 kilometers in radius. The Sun itself has a radius of about 696,000 kilometers. The density implied by that compression is beyond ordinary intuition. There are 3 main categories of black holes. Stellar mass black holes, ranging from about 5 solar masses to roughly 100, form when massive stars exhaust their nuclear fuel. The core collapses catastrophically in a fraction of a second, the outer layers explode as a supernova, and the remaining core, if massive enough, collapses all the way to a black hole. These populate binary star systems throughout galaxies, quietly accreting gas from companion stars and shining brilliantly in X-rays. Intermediate mass black holes, from roughly 100 solar masses to 100,000, are the most poorly understood of the 3 types. They should exist as seeds for supermassive black holes and as the central objects of dense globular clusters, but definitive confirmation has proven difficult for most claimed examples. Supermassive black holes, ranging from millions to tens of billions of solar masses, lurk at the centers of most large galaxies. Our own Milky Way harbors one called Sagittarius A star, with a mass of approximately 4 million times that of our Sun. The supermassive black hole at the center of M87 weighs approximately 6.5 billion solar masses. The recently characterized quasar J 0529-4351 is powered by a black hole of about 17 billion solar masses, accreting so voraciously that its disk alone spans 7 light-years in diameter. Something crucial about black holes that is often overlooked. Most black holes in nature are not static, non-rotating objects. They spin. A spinning black hole, described mathematically by the Kerr metric, after Roy Kerr, who derived its solution in 1963, is fundamentally different in structure from a static Schwarzschild black hole. A spinning black hole drags the space-time around it into rotation through a process called frame dragging. This creates a region outside the event horizon called the ergosphere, where space-time itself rotates faster than the speed of light relative to distant observers. Nothing inside the ergosphere can remain stationary. It is swept along in the rotation of the black hole, whether it likes it or not. The ergosphere is not the event horizon. Objects can still escape from it, but the frame-dragging forces inside it are what make the energy extraction mechanisms that power relativistic jets possible. The spin of a black hole is parameterized by a dimensionless number between 0 and 1, denoted a star, where 0 is a non-spinning Schwarzschild black hole, and 1 is maximal spin. The spin also profoundly affects the accretion disk because it determines the location of the innermost stable circular orbit, the inner edge of the disk, the last place where matter can orbit stably before the plunge region begins. For a maximally spinning black hole, that inner edge can be pushed all the way to the event horizon itself, meaning the disk penetrates much deeper into the gravitational well, converting a much larger fraction of the infalling matter's rest mass energy into radiation. This is why the efficiency of accretions around spinning black holes is so much higher than around non-spinning ones. Now, with that foundation in place, we turn to the central question: why does matter form a disk around a black hole at all, rather than simply falling straight in? Imagine dropping a ball directly toward the center of the Earth. With no sideways motion, it falls straight down. Now imagine throwing it horizontally at the same moment you let it go. It follows a curved arc. Throw it fast enough, and the Earth curves away beneath it. The ball has entered orbit. Gas and matter falling toward a black hole is like an infinite number of balls thrown from an infinite number of directions with an infinite variety of sideways velocities. That sideways velocity, the component of motion that is not directly toward or away from the central object, is angular momentum. Angular momentum is one of the most conserved quantities in physics. If a parcel of gas far from a black hole has any angular momentum at all, then as it falls toward the black hole and its orbit shrinks, that angular momentum must be redistributed. The angular momentum per unit mass scales with velocity times radius. As the radius decreases, the velocity must increase. A figure skater pulling their arms in spins faster. Water spiraling down a drain moves faster closer to the center. Infalling gas spiraling toward a black hole accelerates in its rotation as it gets closer. This is why accretion disks exist. The angular momentum of infalling matter prevents it from falling directly into the black hole. Matter settles into orbit at whatever radius corresponds to its angular momentum, and the distribution of all the infalling matter produces a disk, a flattened, rotating structure, in the plane perpendicular to the net angular momentum vector. Where does the infalling matter come from? For stellar mass black holes in binary systems, the most common source is Roche-Loeb overflow. In a close binary where one star has evolved into a compact object and the other is still normal, there is a critical region around each star where its gravity dominates its companions, the Roche-Loeb. If the companion star expands as it ages and overflows its Roche-Loeb, gas from its outer envelope streams toward the black hole. This stream carries the angular momentum of its original orbital motion in the binary system, wraps itself around the black hole, and forms an accretion disk. Another source is stellar winds, powerful outflows driven by radiation pressure from massive stars. A nearby black hole can capture a fraction of these winds. For supermassive black holes, gas and dust in the central regions of galaxies is channeled toward the nucleus by gravitational perturbations. From galaxy mergers, bars, and spiral density waves, occasionally a star wanders too close on an unfortunate orbit and is torn apart by tidal forces, a tidal disruption event, with roughly half the stellar material falling back to form a transient accretion disk. All of these sources share one consequence. the gas arrives with angular momentum, settles into orbit, and forms a disk. But forming a disk is the easy part. The hard part, the part that puzzled astrophysicists for decades, is understanding why the disk spirals inward at all, rather than simply orbiting indefinitely. For a long time, the mechanism by which matter in accretion disks loses its angular momentum was deeply mysterious. Angular momentum is conserved. Matter orbiting a black hole will simply keep orbiting unless something removes angular momentum and transfers it outward. Only by shedding angular momentum can an inner parcel of gas drop to a lower orbit and ultimately fall into the black hole. The obvious candidate was viscosity, the internal friction of the gas. In an accretion disk, inner gas orbits faster than outer gas, just as Mercury orbits the Sun faster than Neptune. This differential rotation means adjacent layers are always sliding past each other. Viscosity between these layers would allow the faster inner layer to pull the slower outer layer forward, transferring angular momentum outward while mass flows inward. In principle, this drives accretion. The problem was that ordinary molecular viscosity was spectacularly insufficient by many orders of magnitude. If only molecular viscosity acted in accretion disks, matter would take billions of years to spiral from the outer edge to the inner edge. But we observe accreting systems with variations happening on timescales of days and weeks. In 1973, Nikolai Shakura and Rashid Sunyaev published the foundational paper of accretion disk theory. They acknowledged they did not know the physical mechanism driving angular momentum transport, but parameterized their ignorance with a single dimensionless number called alpha. In their model, the effective viscosity is proportional to alpha, multiplied by the disk pressure and sound speed. Alpha is just a number between 0 and 1, encapsulating all the poorly understood physics. Values inferred from observations are typically 0.01 to 0.3. The Shakura-Sunyaev model was remarkably successful at reproducing observations, but it was fundamentally incomplete because nobody could say what physical mechanism produced the required viscosity. There was a crucial clue hiding in the literature, unrecognized for decades. In 1959, Evgeny Velikov studied electrically conducting fluids in rotating magnetic fields and found instabilities under certain conditions. In the early 1960s, Subramanian Chandrasekhar extended this work, showing that a rotating fluid permeated by a magnetic field could become unstable even when the rotation was hydrodynamically stable. Remarkable results, but nobody connected them to the angular momentum problem in accretion disks. That connection was finally made in 1991 by Stephen Balbus and John Hawley. Their paper on what became known as the magnetorotational instability, or the MRI, is now considered one of the most important astrophysics papers of the late 20th century. The physical picture of the MRI is beautiful and can be understood through a simple analogy. Imagine two parcels of gas in an accretion disk, one slightly closer to the black hole and one slightly farther out. They are connected by a magnetic field line. Think of it as a spring. The inner parcel orbits faster than the outer one. As time goes on, the inner parcel pulls ahead. The magnetic field line connecting them gets stretched, creating a tension like a spring under load. This tension pulls the inner parcel backward, slowing it down. When an orbiting object slows down, it loses angular momentum and falls to a lower orbit. It moves inward toward the black hole. Simultaneously, the magnetic spring pulls the outer parcel forward, speeding it up, pushing it to a higher orbit outward. Angular momentum flows from inner to outer, and as the two parcels separate, the spring tension increases, making the transfer go even faster. The instability runs away. Differential rotation amplifies any seed magnetic field into vigorous turbulence throughout the disk, and this turbulence acts as an effective viscosity with alpha values broadly consistent with observations. With the angular momentum transport mechanism understood, we can now tour the disk's physical structure from its cool outer regions inward to its blazing interior. Start at the outer edge. For a stellar mass black hole in a binary system, this might be a few 100,000 to a few million kilometers. For a supermassive black hole fed by galactic gas, the outer disk might extend to scales of parsecs, many trillions of kilometers. At these outer radii, temperatures are relatively modest, a few thousand to tens of thousands of degrees, comparable to the surface of a star. The emission is invisible and near-infrared light. Moving inward, temperature rises steeply. In a standard thin disk, temperature scales roughly as the radius to the -3/4 power. Halve the radius, and the temperature increases by a factor of roughly 5. By the middle zones, temperatures have climbed to hundreds of thousands of degrees, shifting emission into the ultraviolet and soft X-ray bands. This is why active galactic nuclei, the luminous centers of galaxies powered by accreting supermassive black holes, have such strong ultraviolet emission. In the innermost regions, temperatures peak at millions to tens of millions of degrees for stellar mass systems, and the gas is a fully ionized plasma emitting hard X-rays. This is why stellar mass black holes in binary systems shine so brilliantly in X-rays. They can be seen across tens of thousands of light years. The total spectrum of a thin disk, a superposition of blackbody emission from all its annuli, each at the temperature corresponding to its radius, rises steeply in the infrared and optical, peaks in the ultraviolet or soft X-ray, and falls off at higher energies. This characteristic spectral shape is one of the key observational signatures that allows astronomers to identify and characterize accretion disks. Above and below the disk lies the corona, a tenuous region of ultra-hot plasma reaching temperatures of hundreds of millions or even billions of degrees, analogous to the Sun's corona, which is also mysteriously hotter than the photosphere below it. The disk corona is heated by magnetic reconnection events that inject energy faster than it can radiate away. The corona produces hard X-rays through inverse Compton scattering. Hot electrons collide with cooler photons from the disk and kick them to higher energies, producing a characteristic power law X-ray spectrum extending to hundreds of kiloelectron volts. The structure of the disk changes dramatically with accretion rate. The standard thin Shakura-Sunyaev disk applies when accretion is a modest fraction of a characteristic maximum called the Eddington rate. In this regime, the disk is geometrically thin, optically thick, and radiatively efficient. When the accretion rate drops far below the Eddington rate, the disk transitions to an advection-dominated accretion flow, or ADAF. The gas density becomes low enough that heat cannot radiate away efficiently. Instead, it is advected inward and swallowed by the black hole. The disk puffs up into a thick, hot torus. gas temperatures approach the virial temperature tens of billions of degrees for electrons. Sagittarius A star, our own galaxy's central black hole, is currently in such a state. At the opposite extreme, when accretion rates significantly exceed the Eddington limit, the disk inflates into slim disks or radiation-dominated tori, where radiation is trapped inside and advected inward faster than it can escape. Super Eddington accretion is thought to occur in some ultraluminous X-ray sources and in the most rapidly growing black holes in the early universe. Running through all these regimes is one fixed reference point, the innermost stable circular orbit, the ISCO. This is the smallest radius at which a stable circular orbit exists. Inside it, any material is doomed to spiral inward and cross the event horizon. For a non-spinning Schwarzschild black hole, the ISCO sits at 3 times the Schwarzschild radius. For a maximally spinning Kerr black hole with a prograde disk, it can approach the event horizon itself. The radiative efficiency of the disk, the fraction of rest mass energy radiated away as matter spirals from infinity to the ISCO, is about 5.7% for a Schwarzschild black hole and about 42% for a maximally spinning Kerr black hole. Compare these to nuclear fusion. Hydrogen fusing to helium releases only 0.7% of rest mass as energy. Even the least efficient accretion disk outperforms fusion by a factor of 8. A maximally spinning black hole disk outperforms it by a factor of 60. Nothing in nature converts matter to energy more efficiently. These efficiency numbers explain why accreting black holes can produce luminosities that dwarf entire galaxies. The Eddington luminosity, the theoretical maximum at which radiation pressure balances gravity, scales linearly with black hole mass. For a 10 solar mass black hole, it is about 130,000 times the sun's luminosity. For a 10 billion solar mass black hole, it is 130 trillion times the sun's luminosity. When accretion approaches this limit, single objects, called quasars, can outshine every star in their host galaxies. The quasar 3C273, the first quasar identified as such by Martin Schmidt in 1963, shines at about 4 trillion times the luminosity of the Sun from a distance of 2.5 billion light-years, visible through a small telescope. The quasar J0529-4351, identified as the most luminous known quasar, shines at roughly 500 trillion times the Sun's luminosity, powered by a black hole, accreting more than 1 solar mass per day, its disk spanning 7 light-years of space. All of this energy comes from gravity, from the release of gravitational potential energy as matter falls deeper and deeper into a black hole's grip, converted to radiation with an efficiency nuclear physics cannot approach. One of the most spectacular manifestations of black hole accretion appears at first paradoxical, relativistic jets. These are narrow, highly collimated beams of plasma and electromagnetic energy launched outward from the immediate vicinity of the black hole at velocities approaching and sometimes apparently exceeding the speed of light. Jets stream perpendicular to the disk plane in both directions simultaneously, and they can extend for thousands or hundreds of thousands of light-years before dissipating into the intergalactic medium. They carry with them an extraordinary fraction of the total accretion power. In some systems, more energy escapes in the jets than is radiated by the disk itself. The theoretical framework for jets was developed in two landmark papers. Roger Blandford and Roman Zanajek in 1977 described how a rotating black hole embedded in a magnetic field could act as a cosmic unipolar inductor. Inside the ergosphere, space-time rotates at extraordinary angular velocities due to frame dragging. Magnetic field lines threading the ergosphere are dragged around by the rotating space-time, generating an electromotive force that accelerates plasma along the field lines and launches it outward in a collimated beam along the spin axis. The energy source for this jet is not in falling matter, but the rotational energy of the black hole itself for a maximally spinning 10 solar mass black hole. This reservoir contains roughly 10% of the black hole's total rest mass energy, equivalent to the total energy output of the Sun over hundreds of billions of years. The Blandford-Zanajek mechanism taps this reservoir directly, gradually spinning down the black hole as it powers the jet over millions or billions of years. Roger Blandford and David Payne, in 1982, described a complementary mechanism, where Blandford-Zanajek is about extracting energy from the black hole itself. The Blandford-Payne mechanism is about launching material from the disk. Large-scale magnetic field lines anchored in the disk and threading outward can act as magnetic springs for rotating disk material. If a field line makes an angle of less than 60 degrees with the disk plane, centrifugal forces overcome the magnetic tension along the field line, and material is flung outward along it, like beads flying off a rotating wire. Under the right conditions, this wind is collimated into a jet by the hoop stresses of the surrounding magnetic field. Unlike the Blandford-Zanajek mechanism, this can work even for a non-spinning black hole, as long as the disk has a strong ordered magnetic field. Real jets likely involve contributions from both mechanisms, with their relative importance varying depending on the black hole spin and the magnetic field geometry. What is clear from observations is that jets are preferentially launched by rapidly spinning black holes. The correlation between spin and jet power supports the central role of the Blandford-Zanajek mechanism. Strong ordered magnetic flux threading the inner disk also appears to be essential. A class of accretion flows called magnetically arrested disks, where accumulated magnetic flux near the black hole becomes strong enough to occasionally halt accretion itself, appear to be particularly powerful jet producers. The 2019 Event Horizon Telescope polarization measurements of M87 star revealed a large-scale spiral magnetic field pattern in the inner accretion ring, consistent with what is expected near a magnetically arrested disk state. The very configuration theorized to be optimal for jet launching. The jet from M87, the giant elliptical galaxy in the Virgo cluster, is perhaps the most studied example of a relativistic jet in the universe, first observed by Heber Curtis in 1918, who noted a curious straight ray extending from the galaxy's core in photographic plates. This jet extends about 5,000 light-years from the black hole and is visible from radio waves through visible light to X-rays and gamma rays. Long baseline radio interferometry revealed what appeared to be features in the jet moving faster than the speed of light. Apparent superluminal motion, a projection effect that occurs when a jet is pointed nearly at the observer and plasma moves close to the speed of light. The geometry of near-light speed motion combined with a favorable viewing angle makes features in the jet appear to advance across the sky faster than light, though no actual superluminal travel is involved. The 2019 Event Horizon Telescope image of M87 star showed the bright accretion disk ring connecting directly to the base of this jet, finally revealing the physical scale of the structure that powers one of the most dramatic features in the nearby universe. Microquasars, stellar mass black holes in binary systems with jets, offer a complementary perspective at much smaller physical scales. The system GRS 1915 plus 105, discovered in 1994 to be launching plasma blobs at apparent superluminal velocities, contains a roughly 12 to 14 solar mass black hole accreting from a companion star. This system has been one of the most intensively studied X-ray binary systems ever since. Its accretion disk undergoes dramatic oscillations and transitions between different accretion states: hard states with a prominent corona and weak jets, soft states with a bright disk and suppressed jets, and intermediate states with powerful transient jets on timescales of minutes to months. These rapid state transitions have been invaluable for understanding the connection between accretion disk geometry and jet production. Jets also play a profound role at galactic and cosmological scales, as a jet from an active galactic nucleus propagates outward through the surrounding galaxy and into the intergalactic medium. It transfers enormous amounts of energy to its environment. It inflates vast cavities in hot intracluster gas, directly visible as X-ray dark regions in Chandra Observatory images, shaped by the jet like a finger pushing through thick material. The energy injected by jets heats surrounding gas and suppresses its cooling and condensation into new stars. This AGN feedback is now understood to be a critical regulatory mechanism in galaxy evolution, explaining why the most massive galaxies, which sit at the centers of the largest dark matter halos and should have access to the most gas, are not the most star-forming galaxies, but are instead predominantly old, red, gas-poor ellipticals, whose star formation was quenched long ago by the feedback from their central accreting black holes. Without jet feedback, our models of galaxy formation predict far too many massive luminous galaxies compared to what we observe. The jets of accreting black holes have literally shaped the populations of galaxies we see when we look out at the universe. To bring all of this into the concrete, let us take a tour of some of the best-known accretion disks in the universe. Cygnus X1 is where the story of confirmed stellar mass black hole accretion begins. In 1964, rocket experiments briefly lofting X-ray detectors above Earth's atmosphere detected a powerful X-ray source in the constellation Cygnus. Over the following decade, astronomers identified its optical counterpart, a blue supergiant star called HDE 226868. And by measuring how it was periodically pulled toward and away from us by the gravity of an unseen companion, they placed a lower limit on the companion's mass, far too large for any white dwarf or neutron star. By the early 1970s, most astronomers were convinced the companion was a black hole. The famous 1974 bet between Stephen Hawking and Kip Thorne captures the intellectual atmosphere of the time. Hawking wagered against Cygnus X, one being a black hole as an insurance policy, and conceded in 1990 when the evidence became overwhelming. Modern measurements have refined the black hole's mass to approximately 21 solar masses, with a spin parameter greater than 0.99, essentially maximal. The inner edge of its accretion disk sits almost at the event horizon. The disk temperature peaks in the range of hundreds of millions of degrees, producing the brilliant hard X-ray emission that makes Cygnus X1 one of the brightest persistent X-ray sources in the sky. Sagittarius A** occupies the opposite end of the accretion spectrum. This 4 million solar mass black hole, 27,000 light-years away at our galactic center, is extremely quiet by the standards of active galactic nuclei. Its luminosity is roughly 10 billion times lower than you would expect for a black hole of its mass, accreting at even a modest fraction of its Eddington limit. It is surrounded by a dense cluster of stars in very tight orbits, tracked for 30 years with infrared telescopes. The orbital paths of these stars, particularly S2, which completes an orbit in only 16 years, approaching within about 120 astronomical units at closest approach, provided some of the most compelling evidence for a supermassive black hole before direct imaging. Sagittarius A* accretes primarily from the stellar winds of massive stars in the central cluster, producing an ADAF-type flow that is hot, low density, and radiatively inefficient. The Event Horizon Telescope collaboration announced on April 10, 2019, that they had produced the first direct image of a black hole shadow. The target was M87*, and the image showed a bright asymmetric ring surrounding a dark central region. The black hole shadow. The ring brightness was higher on one side due to relativistic beaming. The portion of the disk rotating toward us appears brighter from Doppler boosting. The size and shape were consistent with general relativity's predictions for a 6.5 billion solar mass black hole. The EHT is not a single telescope, but an array of radio dishes across 6 continents: Hawaii, Chile, Mexico, Spain, Antarctica, Greenland, and Arizona, operating simultaneously to create an effective aperture equal to Earth's diameter. The second HT image, released in May 2022, showed Sagittarius A*, far more challenging despite being much closer, because gas near its smaller black hole orbits in minutes rather than the days required near M87*. The resulting image showed a bright ring with a dark shadow, broader consistency with general relativity confirmed in the most extreme gravitational environment ever directly imaged. The history of how human beings came to understand accretion disks spans roughly 60 years of theoretical insight and technological development. A story that moves from speculative proposals about quasar power sources to direct imaging of black hole shadows. In 1964, Edwin Salpeter and Yakov Zeldovich independently published papers arguing that the enormous luminosities of quasars, then newly identified, deeply mysterious objects, could be explained if supermassive black holes were accreting surrounding gas with high efficiency. At the time, quasars were baffling. They appeared point-like in optical images like ordinary stars, but their spectra showed emission lines shifted to enormous redshifts, implying cosmological distances and hence luminosities that no known stellar process could explain. The Salpeter-Zeldovich insight planted the seed of the modern picture, In 1969, Donald Lyndon Bell of Cambridge published a landmark paper arguing not only that quasars were powered by accreting supermassive black holes, but that the inactive remnants of these black holes, dead quasars in his phrase, must be lurking at the centers of nearby normal galaxies, including our own, having exhausted their gas supplies and quieted down. This prediction was extraordinarily prescient. We now know that essentially every massive galaxy harbors a supermassive black hole at its center, and the supermassive black holes in quiet galaxies like the Milky Way are indeed the dormant remnants of what may once have been brilliant quasars. Lyndon Bell's 1969 paper also contained one of the first estimates of the mass of the black hole at the Milky Way's center, a calculation that came within a factor of a few of the modern value determined 30 years later by tracking stellar orbits. The Shakura-Sunyaev alpha disk model of 1973 provided the first detailed mathematical framework for thin disks comparable with observations, and the fully relativistic treatment by Igor Novikov and Kip Thorne the same year extended this to the strong gravity regime near the ISCO. On the observational side, the revolution came with space-based X-ray astronomy. The Uhuru satellite, launched in 1970, was the first dedicated X-ray astronomy satellite. In just a few years, it discovered over 300 X-ray sources, including dozens of X-ray binary systems. Many turned out to be neutron stars, but some, including Cygnus X1, appeared too massive to be anything but black holes. Subsequent observatories, Exosat, Ginga, the Rossi X-ray Timing Explorer, Chandra, XMM Newton, and NuSTAR, built progressively more detailed pictures of disk spectra, timing, and variability. The Rossi X-ray Timing Explorer, operating from 1995 to 2012, detected quasi-periodic oscillations in accreting systems at frequencies corresponding to orbital periods very close to the ISCO, providing a new tool for measuring black hole properties that depended directly on strong field general relativity. The NuSTAR telescope, launched in 2012, for the first time, brought focused imaging capability to hard X-ray energies above 10 kilo-electron volts, enabling direct measurements of the iron reflection spectrum from the inner disk with unprecedented sensitivity. The measurement of black hole spin from X-ray spectroscopy emerged through two complementary methods. Continuum fitting measures the temperature spectrum of the disk and fits it to theoretical models to infer the ISCO location and hence the spin. Iron line reflection. Spectroscopy analyzes the shape of the emission line from iron atoms in the disk, illuminated by hard X-rays from the corona. This line, centered near 6.4 kilo-electron volts, is broadened and skewed by Doppler effects and gravitational redshift in strong gravity near the ISCO, encoding how close the inner disk edge is to the event horizon. These techniques have now been applied to dozens of stellar mass black hole binaries and many active galactic nuclei, building a statistical picture of black hole spin distributions. The Event Horizon Telescope collaboration announced on April 10, 2019, that they had produced the first direct image of a black hole shadow. The target was M87 star, and the image showed a bright asymmetric ring surrounding a dark central region, the black hole shadow. The ring brightness was higher on one side due to relativistic beaming. The portion of the disk rotating toward us, appears brighter from Doppler boosting. The size and shape were consistent with general relativity's predictions for a 6.5 billion solar mass black hole. The EHT is not a single telescope, but an array of radio dishes across 6 continents: Hawaii, Chile, Mexico, Spain, Antarctica, Greenland, and Arizona, all observing simultaneously to create an effective aperture equal to the diameter of Earth, achieving angular resolution sufficient to image the accretion ring at a distance of 53 million light-years. The data from all sites were recorded on hard drives and physically shipped to correlator facilities, where they were combined using the technique of very long baseline interferometry. The second EHT image, released in May 2022, showed Sagittarius A star, the first image ever of the black hole at the center of our own galaxy. This was far more challenging to produce despite our galactic center being enormously closer. The difficulty was that Sagittarius A star changes significantly during observations. Gas near M87 star, which is 6.5 billion solar masses, takes weeks to orbit once. Gas near Sagittarius A star, only 4 million solar masses, orbits in minutes to hours. The emission region was blurring and shifting even during a single night of observations, like trying to photograph something moving quickly. The solution required sophisticated averaging and modeling techniques developed specifically for this problem. The resulting image showed a bright ring with a dark shadow, confirming general relativity in the most extreme gravitational environment ever directly imaged and providing the first direct view of the accretion environment at the heart of our own galaxy. And so we come to the edge of everything, the innermost boundary of the accretion disk, the place where the orderly spiral ends and the plunge begins. At the ISCO, the physics of stable circular motion ceases to function. A particle at the ISCO is in the last position where a small perturbation inward produces a restoring force. Any closer to the black hole, and the orbit becomes unstable. A small perturbation sends the object on a tightening downward spiral from which there is no recovery. Once matter crosses the ISCO, it accelerates dramatically. In the plunge region, the orbital velocity is already a substantial fraction of the speed of light, and matter is essentially in free fall from that point inward, gaining kinetic energy rapidly as it descends into the deepening gravitational well. Time dilation becomes severe. Clocks near the inner disk run measurably slower than those far from the black hole, and the effect becomes extreme as the event horizon is approached. An outside observer watching a particle fall from the ISCO would see it slow down and redden as it approached the horizon, its image freezing and dimming as photons from closer and closer to the horizon take exponentially longer to climb out against the increasingly intense gravity. For matter falling toward a stellar mass black hole, tidal forces, which arise because the gravitational pull on the near side of an extended object is stronger than on the far side, become enormous well before the horizon. A person falling toward a stellar mass black hole would be stretched radially and compressed laterally long before reaching the event horizon, a process called spaghettification. The differential tidal forces across a human body at the event horizon of a 10 solar mass black hole would be millions of times greater than Earth's surface gravity, utterly catastrophic. Gas and dust falling into stellar mass black holes are stretched into long, thin streams and heated violently by compression and friction before they reach the disk. For a supermassive black hole of billions of solar masses, however, the event horizon is so enormously large in physical scale, its radius may be measured in billions of kilometers, that tidal forces at the horizon are relatively mild. A person falling into a billion solar mass black hole would cross the event horizon with no particular physical sensation, not knowing they had entered a region from which no return was ever possible. The singularity would still lie in their future, but the horizon itself would pass without drama. The event horizon itself is not a material surface. It is a mathematical boundary, a point of no return defined by the causal structure of space-time. To a local observer falling through it, nothing special happens. There is no wall, no flash, no alarm sounding in the geometry of space-time at that exact moment. But from far away, the infalling observer appears to slow down, redden, and freeze at the horizon, never quite crossing it in any finite amount of the outside observer's time. These two perspectives, the falling observers and the distant observers, are both entirely valid in general relativity, describing the same physical situation from different reference frames. The causal disconnection between inside and outside means no experiment can ever directly compare the two views, and the apparent paradox dissolves into the geometry of curved spacetime. The information paradox, and whether information about the quantum state of infalling matter is truly lost when it crosses the horizon, or somehow encoded in the Hawking radiation that black holes emit through quantum effects, remains one of the deepest unsolved problems in theoretical physics. Stephen Hawking predicted in 1974 that black holes should emit faint thermal radiation through quantum processes at the horizon. For a stellar mass black hole, this Hawking radiation temperature is billionths of a degree above absolute zero, completely undetectable with any current instrument. But the principle is profound. Black holes are not truly black. They glow ever so faintly, and in doing so, they may carry away information about what fell in, or so some theorists argue. Whether information is fully preserved, partially preserved, or genuinely destroyed remains at the frontier of physics, connecting quantum mechanics and general relativity in ways neither theory alone can resolve. Accretion disks are, in this sense, not just fascinating astrophysical structures. They are gateways to the deepest questions in physics. They are where thermodynamics, fluid dynamics, electromagnetic theory, nuclear and atomic physics, special relativity, and general relativity all converge at once in conditions that cannot be reproduced in any laboratory on Earth. They force us to use every tool of modern physics simultaneously, testing each against the others in the most extreme environments the universe provides. And in doing so, they reveal the places where those tools work perfectly and the places where they do not yet fully agree. Think about what this all adds up to. The universe began 13.8 billion years ago in a state of extraordinary simplicity, hot, dense, smooth plasma expanding uniformly in all directions. Over billions of years, tiny density fluctuations grew under gravity into galaxies and filaments. Stars ignited and burned and died. Black holes formed from the most massive stars or assembled at galactic centers from infalling gas. And around many of those black holes, the inevitable consequence of angular momentum. Conservation produced accretion disks, structures that are in some ways the most information-rich environments in the universe. The spectrum of light from an accretion disk carries signatures of the black hole's mass and spin. The variability of that light traces the orbital dynamics of matter in extreme gravity. The polarization encodes the magnetic field geometry. The jets carry information about spin and magnetic flux. Every photon that escapes the inner disk before crossing the horizon carries away some piece of the story of what is happening there. And we, on our small planet orbiting an ordinary star in one spiral arm of one galaxy among 2 trillion, have developed the mathematics and technology and collective determination to decode these messages. We have identified black holes from companion star orbits. We have measured their spins from iron emission lines. We have caught the moment a star was torn apart and watched a disk form from its debris. We have synchronized telescopes across 6 continents to image a black hole shadow for the first time in history. We have built gravitational wave detectors sensitive enough to measure distortions in space-time, smaller than 1,000th the diameter of a proton. And we have heard the final inspiral of black holes billions of light years away. The mysteries that remain are profound. We do not fully understand how jets are collimated over the enormous scales on which they are observed, stretching coherently from near the event horizon to hundreds of thousands of light years away, without dispersing into the surrounding medium. We do not have a complete physical theory of the corona, how it forms, how it maintains its extraordinary temperature, and what determines its geometry relative to the disk. We do not know what lies at the singularity, where our equations predict infinite density and simply stop being useful. We do not know whether information carried by infalling matter is truly lost or somehow preserved. We do not know precisely how the spins of supermassive black holes are built up over cosmic time, whether they are spun up primarily by accretion from a sustained disk or spun down by retrograde accretion events, or shaped most fundamentally by major mergers. These open questions are not failures, they are invitations. Every answered question about accretion disks has revealed a deeper question beneath it, and every new generation of instruments has turned questions that once seemed permanently beyond reach into tractable problems of observation and theory. Looking forward, the tools we have are only the beginning. Plans for a next-generation event. Horizon Telescope. Incorporating more stations, operating at shorter radio wavelengths to achieve higher resolution, and potentially including space-based elements to extend the baseline beyond the diameter of Earth. Promise images that could trace the jet launching region directly. Mapping the magnetic field structure in the innermost accretion flow with detail never before achieved. The laser interferometer space. Antenna LISA, a proposed space-based gravitational wave detector to be launched in the 2030s, will detect gravitational waves from supermassive black hole binary inspirals and from extreme mass ratio inspirals, systems where a stellar mass object slowly spirals into a supermassive black hole, tracing the geometry of curved space-time around it with exquisite precision. Each orbit of the smaller body traces the space-time metric, and thousands of orbits worth of gravitational wave data will build up a map of the black hole's space-time with a precision that no electromagnetic observation can match. These future observations will test the physics of accretion and strong field gravity in ways that are currently impossible. The next time you look up at a clear night sky, consider what you cannot see. in every direction, scattered among the familiar stars. Black holes are feeding. Gas is spiraling inward along trajectories shaped by angular momentum conservation. Magnetic fields are amplifying and tangling through magnetorotational instability, driving the turbulence that transfers angular momentum outward and allows mass to fall inward toward the event horizon. Somewhere out there in the darkness, a star is being torn apart by tidal forces, and its debris is wrapping itself into an accretion disk for the very first time, a glowing ring of stellar wreckage around a black hole that was dark a year ago and blazing now. Somewhere, jets of plasma are being launched by spinning black holes and the twisted magnetic fields of their ergospheres, streaking outward at nearly the speed of light to pour energy into the surrounding gas of their host galaxies, suppressing star formation, heating intergalactic gas, shaping what the galaxy will look like billions of years from now. Matter is racing toward event horizons at fractions of the speed of light, converting gravitational energy into radiation with an efficiency that nuclear fusion cannot approach. The universe is perpetually burning, not with fire or fusion, but with the slow, relentless work of gravity on infalling matter, in disks of superheated plasma that glow in wavelengths our eyes were not built to see. The sky looks quiet. It is anything but. It is happening right now, all around us, in perfect silence. If this journey through one of the most extraordinary phenomena in the universe resonated with you, please consider pressing like and subscribing to the channel. Every subscription helps this channel continue crafting these slow, deep explorations of the cosmos, the kind of journeys that don't rush past the detail, that sit with the strangeness and the beauty of the universe for as long as it deserves. There is so much more to explore. Come back whenever you are ready. Until then, take care of yourself and keep wondering about what lies beyond the edge of the visible. Good night.